Hello, everyone. Welcome to our Deep Dive podcast, where we review the latest and greatest in AI research. Today, we're exploring the GLM 4.5 paper titled GLM 4.5 Agentic, Reasoning and Coding ERC Foundation Models from Zhipu AI and Tsinghua University. Are you ready to get started?
Absolutely. GLM 4.5 has been making waves in the open-source LLM community. With its mixture of experts, MAUI architecture, and a whopping 355 billion total parameters, it's a fascinating model. But before we get into the technical details, can you give us a high-level overview of what makes GLM 4.5 special?
Of course. GLM 4.5 is designed to excel in three interconnected areas: agentic abilities, complex reasoning, and advanced coding. The model supports both thinking and direct response modes, which means it can deliberate for complex tasks or respond instantly for simpler ones. This hybrid reasoning approach is a key innovation.
That's interesting. So it's not just about being big, but also about being flexible in how it reasons and responds. How does GLM 4.5 compare to other leading models in the field?
Great question. According to the paper, GLM 4.5 achieves strong performance across 12 major benchmarks, including TAOU Bench, AIME 24, and SUCB Bench Verified. It ranks third overall among all evaluated models and second on agentic benchmarks, despite having fewer parameters than some competitors.
That's impressive efficiency. I noticed there's also a smaller version called GLM 4.5 Air, with 106 billion parameters. How does it perform compared to the full model?
GLM 4.5 Air is quite competitive, especially for its size. It matches or exceeds other models in the 100B parameter range, like Qwen 3-235B and Minimax M1. On the ERC benchmarks, it ranks 6th overall, which is remarkable for a compact model.
Let's talk about the architecture. You mentioned it uses a mixture of experts design. Can you explain what that means and why it's important?
Sure. In an MLE architecture, the model consists of multiple experts, or subnetworks, and only a subset of these experts are activated for each input. This allows the model to scale up in total parameters without a proportional increase in computation for each inference. GLM 4.5 has 355B total parameters, but only 32B are activated per input.
That's a clever way to balance scale and efficiency. The paper also mentions loss-free balance routing and sigmod gates for the MAUI layers. What are those?
Loss-free balance routing is a technique to ensure that all experts are utilized evenly, preventing some from being overused while others are underused. Sigmoid gates help in selecting which experts to activate for a given input, making the routing process more flexible and stable.
I see. The architecture section also highlights some unique choices, like increasing the number of layers and attention heads. Why did the authors make these changes?
The authors found that deeper models, with more layers, exhibited better reasoning capacity. They also increased the number of attention heads to 96 for a 5120 hidden dimension, which, while not improving training loss, consistently improved performance on reasoning benchmarks like MMLU and BBH.
That's fascinating. What about the pre-training data? What sources did they use, and how did they ensure quality?
The pre-training corpus is diverse, including web pages, social media, books, papers, and code repositories. They used quality scoring and upsampling for high-quality documents and applied semantic deduplication to remove redundant or low-value content. For code, they curated data from GitHub and other platforms, filtering for quality and using a fill-in-the-middle training objective.
It sounds like a very thorough data pipeline. The paper also mentions a multi-stage training process, including mid-training. What does that involve?
After the initial pre-training, mid-training focuses on domain-specific datasets to boost performance in key areas. This includes repo-level code training, synthetic reasoning data, and long-context agent training. Sequence lengths are extended up to 128K tokens during this stage to improve long-context understanding.
That's a huge context window. How did they handle optimization and hyperparameters during training?
They used the muon optimizer for most parameters, with a cosine decay learning rate schedule. Batch size was gradually increased, and regularization was applied via weight decay. For long context modeling, they adjusted ROPE's base frequency and used best fit packing during mid-training to avoid truncating important sequences.
Now let's move to post-training. The paper describes an expert model iteration process. What does that entail?
Post-training is divided into two stages. First, they train expert models specializing in reasoning, agentic tasks, and general chat. Then, they use self-distillation to integrate these experts into a unified model capable of both deliberative reasoning and direct responses.
Supervised fine-tuning (SFT) is mentioned as a key step. How is SFT used in this context?
SFT is used at the start of both expert training and unified training. Initially, it provides a cold start to give each expert basic capabilities. Later, it distills the strengths of each expert into the main model, ensuring it can handle a wide range of tasks with both deep reasoning and quick responses.
The function call template using XML-like tags is an interesting detail. Why did they move away from JSON for function calls?
JSON requires a lot of character escaping, especially when code is involved. By using XML-like tags, they reduce the need for escaping, making it easier for the model to generate and process function calls, especially in agentic scenarios.
That's a practical improvement. The paper also discusses rejection sampling and prompt selection. How do these contribute to model quality?
Rejection sampling filters out low-quality or invalid samples from expert models, ensuring only high-quality data is used for training. Prompt selection focuses on challenging prompts, and response-level scaling generates multiple responses per prompt, further improving performance on difficult tasks.
Let's talk about reinforcement learning. The paper introduces several RL strategies, including difficulty-based curriculum learning. How does this work?
During RL, the model's proficiency changes, so static data can become too easy or too hard. The two-stage curriculum starts with moderate difficulty and then switches to extremely difficult problems, ensuring the model continues to improve and doesn't plateau.
They also mention single-stage RL at 64K output length. Why is this better than multi-stage RL with increasing lengths?
Multi-stage RL with shorter lengths can cause the model to unlearn its long context capabilities. By training directly at the full 64K length, the model maintains and improves its ability to handle long outputs, leading to better final performance.
The paper includes ablation studies for code and science RL. What were the key findings there?
For code RL, using a token-weighted mean loss accelerates convergence and provides a more stable gradient signal. For science RL, training exclusively on high-quality, expert-verified data yields the best results, highlighting the importance of data quality.
Dynamic sampling temperature is another technique they use. How does it help?
Adjusting the sampling temperature during RL maintains a balance between accuracy and exploration. When the model's outputs become too predictable, increasing the temperature encourages diversity, while a quality control mechanism ensures performance doesn't drop.
The agentic RL section is quite detailed. How do they collect and synthesize data for agent tasks?
For web search and information-seeking tasks, they use a pipeline that combines multi-hop reasoning over knowledge graphs and human-in-the-loop extraction. For software engineering, they curate GitHub pull requests and issues, running evaluations in a sandboxed environment for safety and scalability.
Iterative self-distillation is used to push performance further. Can you explain how that works?
After initial RL training, they use the improved model to generate new SFT data, replacing the original data. This creates a better SFT model, which is then further improved with more RL training. This iterative process efficiently pushes the model's capabilities.
The RL infrastructure, called SLIME, supports both synchronous and asynchronous training. Why is this flexibility important?
Different RL tasks have different requirements. Synchronous training is efficient for general tasks, while asynchronous training is better for agentic tasks with long or variable trajectories. The infrastructure allows both, maximizing resource utilization and throughput.
They also use mixed precision inference, specifically FP8, to accelerate rollouts. How does this impact training?
FP8 inference significantly speeds up data generation during rollouts, which is often a bottleneck in RL training. This allows for faster policy updates and more efficient use of computational resources.
Let's move on to evaluation. How does GLM 4.5 base perform compared to other open source base models?
GLM 4.5 base is stable across English, code, math, and Chinese benchmarks, validating the goal of unifying multiple abilities in one model. It performs competitively with other large MLE models, despite having fewer activated parameters.
On the 12 ERC benchmarks, how does GLM 4.5 stack up?
GLM 4.5 ranks third overall and second on agentic tasks. It outperforms Gemini 2.5 Pro and is close to Claude Sonnet 4 on TAU Bench. On BFCL v3, it achieves the best overall score, and on BrowseComp, it's close to the second best model.
What about reasoning benchmarks like AIME24 and GPQA?
GLM 4.5 outperforms OpenAI 03 on AIME24 and Scicode, and on average, it's better than Claude Opus 4 and close to DeepSeek R1-0528. Its performance on Math 500 and LCB is also strong.
Coding is another key area. How does GLM 4.5 perform on Cevo Bench Verified and Terminal Bench?
On Cevo Bench Verified, GLM 4.5 outperforms GPT 4.1 and Gemini 2.5 Pro, and on Terminal Bench, it beats Claude Sonnet 4. Overall, it's a top competitor for coding tasks.
The paper also evaluates general abilities using benchmarks like MMLU and SimpleQA. How does GLM 4.5 fare?
On MMLU, GLM 4.5 is on par with other flagship models. On SimpleQA, it performs similarly to DeepSeek v3 and R1, despite having fewer parameters. It also does well on IFEval, Sysbench, and Multi-Challenge.
Safety is a critical concern. How does GLM 4.5 perform on Safety Bench?
GLM 4.5 achieves a strong safety score, comparable to Kimi K2 and GPT 4.1. It excels in ethics and morality, mental health, and physical health, though there's room for improvement in unfairness and bias.
The authors also conducted hands-on human evaluations. What were the results there?
In English, Chinese, and other languages, GLM 4.5 achieved the highest overall scores, especially in mathematics, text generation, and logical reasoning. It also excelled in agentic coding tasks with the highest tool calling success rate.
The translation evaluation is particularly interesting. How does GLM 4.5 handle challenging real-world translation cases?
GLM 4.5 significantly outperforms specialized translation models on 100 challenging cases, demonstrating a deep understanding of internet slang, cultural context, and domain-specific terminology.
That's a testament to its generalist capabilities. As we approach the end of our review, what are the main takeaways from the GLM 4.5 paper?
GLM 4.5 and GLM 4.5 Air represent a significant step forward in open-source LLMs. With their MLE architecture, hybrid reasoning modes, and strong performance across agentic, reasoning, and coding tasks, they set a new standard for parameter efficiency and versatility.
The open release of both models and the evaluation toolkit is also a big contribution to the research community. It enables reproducibility and further innovation.
Absolutely. The paper demonstrates that with careful architecture design, data curation, and training strategies, it's possible to build models that are both powerful and efficient, capable of handling a wide range of real-world tasks.
That wraps up our deep dive into GLM 4.5. Thanks for joining us on this journey through one of the most exciting developments in large language models. Any final thoughts?
Just that GLM 4.5 is a milestone for open-source AI, showing that you don't need the largest model to achieve top-tier performance. We look forward to seeing how the community builds on this work.
Me too. Thanks for listening, everyone. Stay tuned for our next episode where we'll review another cutting-edge AI paper. Until then, keep learning and exploring.
To summarize, GLM 4.5 introduces a highly efficient, open-source mixture of experts language model that excels in agentic, reasoning, and coding tasks, setting new benchmarks for performance and versatility in the LLM landscape.